Welcome to the session on signals and system. Here today we will discuss the basic signals first. Before that, basic signals will go for the definitions of signals and system. So we'll try to understand what is signal and what is system. So first of all, we'll go for the signals. So a signal is nothing but it's a function of one or more variables that conveys the information. When that function is having only single variable, it is called as one-dimensional signal. And the example for one-dimensional signal is a speech signal. If suppose the function is having two or more variables, it is called as a multi-dimensional signal. And the example is like a image. Image is a two-dimensional signal. Okay, so like these are some more examples of signals: power, speech, ECG, sound, flow rate, etc., etc. Then, yeah, generally the independent variable which we want to consider in the signal system for a particular signal is a time. Okay, but the independent variable could be density, it could be porosity, okay, it could be altitude, it could be temperature, it could be anything. Okay, but for signals and system, we will consider the independent variable as time. Fine. So let us go further and let us try to understand what is system. Okay, so we'll understand the system by using one example. Let's consider a black box. Let's consider that black box is like a adder. Okay, so it will have some inputs. So adder will have some inputs. Let's say that those inputs are A, B, C, and D. And let's consider it as it is an adder. It will add all these inputs. So you can see here that this adder, its output is 5, and it is going to add A, B, C, D inputs. Okay, so now this adder is a system, and how can I define my system then? You can see here this A, B, C, D are nothing but the signals to be processed. This Y is nothing but the signal which is newly produced, and this adder is nothing but a system. So how can I define a system now? The system, I can define it like is something like entity that manipulates one or more signals. So these are the one or more signals. To accomplish a function, it is going to accomplish the adder function and producing the new signal. So it is going to produce the Y as a new signal. So system I can define as an entity which manipulates one or more signals to accomplish a function producing the new signal. So this is what is the system. Now let us go further and let us try to understand some basic signals here. So first of all, we'll go for the unit impulse signal. So before going towards the unit impulse signal, exactly, we'll listen one video here. I will just click it on this example. Okay, so just now we have seen the example, or we have seen the video of lightning. So it's suddenly coming and going. Okay, so this can be considered as one of the example for unit impulse signal in continuous time, because it is suddenly coming in, it is vanishing afterwards very soon. Okay, so that's what is the simple example which you can consider for the unit impulse signal. So the signal will appear and immediately it will be vanished. So this is what is the actual signal look like for the unit impulse signal. You can see here it's delta of t, and you can see that it's mathematical expression would be like delta of t equal to 0 for t not equal to 0, and integration of delta of t dt is equal to 1. So whenever we are defining the unit impulse signal, we should define the unit impulse signal by these two equations. This is equation number 1 and this is equation number 2. That is delta of t equal to 0 for t not equal to 0, and integration of delta of t dt will be equal to 0. So these two equations are necessary to define the unit impulse signal. Now, if I want to generate, now this delta of t is not a physically reliable signal. So this delta of t can be generated by using a rectangular pulse of unit area. So if I consider the rectangular pulse like this, you can see here its width is delta and its height is 1 by delta. So ultimately its area would be 1. Okay. So I have just mentioned here that its area is 1. Now let us consider, now we have considered its width is delta. Now let us consider that its width is decreased. Okay, if I decrease the width, and still if I want to maintain the area equal to 1, what I should do? I should increase the height. So if my width is decreased, my height will get increased, because so as to maintain my area equal to 1. Again, if I decrease the width, again the height will increase and my area would be equal to 1. So if my width tends to 0, then my height tends to as large as possible. Okay, width tends to 0 means width is as small as possible. Then height tends to infinity means height is as large as possible. So this is nothing but the representation of unit impulse signal. So in this way, I can generate unit impulse signal from the rectangular pulse. So this is what is the representation of unit impulse signal for the continuous time version. Now let us go for the discrete time. For discrete time, it's very simple. The discrete time, you can write its notation as delta of n is equal to 1 for n equal to 0, and it is equal to 0 for other values. Okay, and if you see the physical significance, then physical significance for this unit impulse signal is nothing but it is useful for finding the responses of the sudden changes like voltage spikes. Okay, like that lightning in the sky. Okay, so this is what is the physical significance for the unit impulse signal. Now let us move further and let us see some properties of unit impulse. So very first property, very important property first is integration of delta of t dt is equal to 1. That is area under unit impulse is going to be equal to 1. So that is the one of the basic and one of the important property which you should consider here. So let's consider one narrow pulse p delta of t whose width is delta lambda and height is 1 by delta lambda, so as to maintain the area equal to 1. So that you can see here its width is delta lambda and its height is 1 by delta lambda. Okay. So this pulse we have considered, this narrow pulse we have considered, and we can represent it mathematically like this: p delta of t is equal to 1 by delta lambda for t in between 0 to delta lambda, and it is equal to 0 for t greater than delta lambda. Now, if I want to represent the impulse signal, how can I write delta of t? I can represent as p delta of t limit delta lambda tends to 0. Okay, so if I'll integrate on both sides and if I'll solve it mathematically, so ultimately at the end I will get this proof, that is integration of delta of t dt is going to be equal to 1. That is area under delta of t, area under unit impulse is going to be equal to 1. Let us move towards the next property. Delta of t is equal to 1 by mod a delta of t. Again, we'll consider the two pulses. One is p delta of t and another pulse. You can see here p delta of t. It's a narrow pulse, and then we'll consider p delta of at, which is a time scaled version of p delta of t. Width delta lambda, height 1 by delta lambda, so as to maintain the area equal to 1. And here width is delta lambda by a and height is 1 by delta lambda. Okay, so let us consider these two pulses. So you can see here these are the two pulses which were considered. It's the original narrow pulse, and it's a time scaled version of this original narrow pulse. Okay. So let us try to prove this property. Let us start with this p delta of t, whose expression I can write it in this way, and for this p delta of at I can write the expression like this. Now if I want to represent the unit impulse signal, this unit impulse signal I can represent as delta of t is equal to limit delta lambda tends to 0 of p delta of t. And the same thing I can write here as p delta of, delta of at is equal to p delta of at with limit delta lambda tends to 0. So if we'll integrate on both sides, and if we'll go on solving it, so at the end, we can get this proof that is delta of at is equal to 1 by mod a delta of t, and that is what is the proof. Let us move towards the third property. Integration x of t delta of t dt is equal to x of 0. You can start with the left hand side, and as you can see, the delta of t is present, or this delta of t exists only at t equal to 0. So ultimately, I can replace this x of t with x of 0. So, and if I'll solve this, now this x of 0 is nothing but a constant with respect to this integration. So x of 0, I can take it outside. So remains, what remains is this integration delta of t dt, and that delta of t dt integration is equal to 1. So ultimately, what I'm getting is x of 0. So this is the proof. On the similar line, I can go with the second or fourth property, x of t delta of t minus t0 dt is equal to x of t0. You can again start with the left hand side. Again, you can see this delta of, now here it is delta of t minus t0. So this delta of t minus t0 exists at t equal to t0 only. So I can write here x of t0. And now again, this x of t0 is a constant for me. If I'll consider the integration with respect to time, so that x of t0 I can take it outside. So what remains in the equation is like integration of shifted version of delta of t dt. So that again, integration is going to be equal to 1. So ultimately, what we will get as right hand side as x of t0. Okay. So this is what is the four properties of unit impulse signal. Now let us go towards the unit step signal. Okay. So the name indicates, the name itself indicates it's a step. Okay. So here I have just shown you the example of staircase. Okay. So it is not the unit step, but it is something like this. Means unit step is like a step. So you can see here, so this is my unit step signal. And why it is unit? Because its amplitude is 1. Okay. So if we'll say this, and if suppose I will consider its amplitude as 1, then I can call this as unit step signal. Unit step signal, because now here the amplitude is 1, you can see here. The signal is something like this, then you can call it as the unit step signal. Okay, fine. So let us see its expressions and its significance now. Let's go with the continuous time. So you can see here, this is the unit step signal. You can see its amplitude is 1. Let's see, and it is represented as e of t. And its expression, you can see here that e of t is equal to 1 for t greater than 0, and it is equal to 0 for t less than 0. And also it is undefined for t equal to 0. Okay, fine. Now let us go towards its discrete time version. So it's u of n, and it would be like this. So you can see here its expression is u of n is equal to 1 for n greater than or equal to 0, and it is equal to 0 for n less than 0. Okay, so this is what is the discrete time unit step signal. Okay, and its physical significance, you can see here that it is useful for finding the response time of the system. Means how quickly the system responds to my input, that I can find out using this unit step signal, by using this unit step signal. Okay, well, let us move further. Now next is the unit ramp signal. So now you can see, everybody knows that what is ramp and how it looks like. So it's nothing, it's a ramp, it's not a unit ramp. Okay, it's a ramp signal. When I can call it as a unit ramp signal, when this height is equal to this length. Okay, if this and this both lengths, if suppose this is x and if this is also x, then I can call it as a unit ramp signal. Okay, means what? Here the unit means it's a slope. Okay, if the ramp is having unit slope, if the slope of the ramp is 1, then you can call that ramp as a unit step signal. I'm just showing this ramp here for just understanding what is ramp. Okay, but if it is unit ramp, only if this height and this length both are same, then only I can call this ramp as a unit ramp signal. Fine. So let us see now its continuous version, continuous time version. So you can see here its expression, we can write it as R of t is equal to t for t greater than 0, and it is equal to 0 for t less than 0. So this is the expression for the unit ramp signal. Its discrete time version, its discrete time version is indicated by UR of n, and its expression I can write it as UR of n is equal to n for n greater than or equal to 0, and it is equal to 0 for n less than 0. So let us go for its significance. You can see here its significance is it is useful for finding the response of the system for linearly rising inputs. Okay, if I'm applying the linearly rising inputs to some system, then how the system will respond to me, that I can find out by using these ramp signals. Okay, fine. So let us go towards the fourth and today's last signal probably. So it is rectangular pulse. So actually rectangular pulse is nothing but it's like a window. Okay, so for understanding, you can see here. So it's a board which is uh, there outside the restaurant. So what it is mentioned here? It is mentioned that it's open between 10 a.m. to 8 p.m. So it's a window. Okay, in between this window only the restaurant will be open. So rectangular pulse is nothing but the simple window. Okay, between the window only the signal exists, and outside that window the signal simply doesn't exist. Simply its value is 0. Okay, so that's what is the simple example of rectangular pulse. Means it's simply a window. Okay, so now let us see its mathematical expression. So it is like this. You can see here that is if you can see here its weight is capital T. Let me just use some another pen, another color. So its width is T and its height is A. Its variable is T. And if I'll name it as x of t, so x of t would be equal to A amplitude of the pulse, rect of t is the variable, and upon capital T is the width of my window or width of my pulse. Okay, so A rect of t by capital T is the representation of my rectangular pulse. It is equal to capital A for this width, that is minus t by 2 to plus t by 2, and it is equal to 0 for other values. So this is the way I can represent the rectangular pulse. Okay, fine. So let's stop here today. We'll just meet in the next turn with some another signals. Thank you very much.